Okay, this video is to show you how to use the TVM solver on the calculator, which I just realized I misspelled, but we'll have to deal with that. The TVM solver lets us find compound interest. We've already talked about simple interest, where the interest is only paid one time at the end of the entire period of the loan or the savings account. But in the case of the TVM solver and compound interest, we're talking about interest that's paid on the amount that's there plus the interest that accumulates. And the compound interest routine can be found using the finance function of the calculator. Now, the one that I have in the video here is a TI-83, and on the TI-83 I turn it on and I'm going to clear it off, and what I do to access the TVM solver is I press the second and the X to the -1 key and I choose TVM solver. That's the finance function on the calculator. Notice above the X to the -1 it says finance in yellow. So I'm going to choose the TVM solver and hit enter. Now, if this were the TI-83 Plus or the TI-84, rather than hitting second and X to the -1, you would hit apps and then select number 1, which is finance, and you would come to the same place, to this TVM solver. So what does this thing do? When you select the TVM solver, N is equal to the total number of compounding periods or payments. Compounding periods means how often does it compound interest, either on your loan or on your savings account or your investment, or how often do you actually pay into it, and those actually need to be equal. So actually it's going to be, to find what N is, you take the number of years for the investment or the loan and multiply it times C/Y, which is C/Y here at the bottom of the page, how many times of compounding per year. And again, I noted here that P/Y and C/Y should be the same. /Y means per year. The second thing we have is the interest rate. Notice that it actually spells out here that that should be a percentage, so we're going to enter. We don't have to change our interest rate into a decimal to be able to use it. We're going to put it actually in as a percentage. Don't get too hung up on PV and FV. Present value and future value can be kind of confusing terms when you're thinking strictly in terms of that terminology. So what we're going to try to think of is that the present value, or PV, is the amount of money you have to begin with. It's the amount that you borrow, the amount that you put on deposit to start with. If you don't put a lump sum on deposit and you actually want to deposit payments, or you want to make payments on a loan, then you would not have a present value, a before value. You would have payment amounts. The future value is the amount that you have after all is said and done. So it's the amount that's at the end of the investment period or the loan. And of course we said P/Y is the number of payments per year, and C/Y is the number of compoundings per year, which should be equal. Now, one thing to notice before we actually try working a problem, you enter cash inflows, in other words, money that you are taking in, you yourself are taking in, the person that holds the account takes in. Those numbers are positive. And cash outflow, which would be amounts of money that you deposit or that you pay out, such as your lump sum payment or your payment amount each payment period, those are going to be entered as negative because you're actually spending that money. So this is money that's paid, and this is money you're basically having go out of your cash. You have to enter all the known values and place the cursor on the value you want to solve for. And once you've done that, you hit alpha enter to access the solve function, and the calculator will do all of the arithmetic for you, which makes it really important that you know what all of the values are that you are going to enter. And that's what we're going to need to practice with. So one of the questions that we come up with is, what are some common compounding periods? Well, one common compounding period is annually. If you deposit annually and your payments are, your interest is compounded annually, then that's once per year, because annually means a year. Semi-annually means twice per year. Every 6 months would be twice per year. Quarterly is 4 times per year. Monthly, there are 12 months in a year, therefore monthly would be 12 payments and compoundings per year. Daily is 365 because there are 365 days in a year. Now the one that you're going to be curious about is, where did I get this horrible looking number for continuous? But if you take 365 days per year and multiply that by 24 hours for each of those days, and then multiply that by 60 minutes for each of those hours, so in other words, 365 days time, wrong place. 365 days in 1 year times 24 hours in 1 day times 60 minutes in each hour means that there are 525,600 minutes in a year. So continuous compounding, without getting too technical, that would be compounding every single minute of every single day. And the number that we would use for continuous compounding then is 525,600, and that will allow you to solve problems 5 and 6 in lesson 2 that we didn't get to finish on the first step of this unit. So then the next thing we do is we're going to look at an actual problem. Now there's another thing the calculator actually does. We will come back to this. We can use the calculator to solve for something called the APY. I'm going to skip over this slide right now and come back to this particular kind of problem as we get to it in lesson 3. So let's look at an example of how we can use the calculator to solve what's called an annuity problem. An annuity is a kind of a savings account. Most people can't put a lump sum of money in to be able to hang on to until they retire, because they're too busy trying to live from day to day and week to week during the current time. But if you want to save for retirement, most people can't afford to put away a small amount of money every week or every month. So an annuity is a series of equal periodic payments, and one of the purposes of an annuity would be a savings account for when you retire. The payments are made at the end of the month, creates what's called an ordinary annuity. So the end of the month goes with ordinary. Payments made at the beginning of each period is called an annuity due. Now the difference between the two, although it really won't come up to haunt you very often, the difference between the two is an ordinary annuity, you get interest on every single payment you make except the very last one. Whereas with an annuity due, you get interest on every single payment you make because you're making your payments at the beginning of the period. So at the end of the first period, you have your payment plus the interest on that payment to go into the next period. Don't worry too much about the distinction between those two though. We assume that payments and compounding periods are the same. We said that several times. Payments per year, compounding periods per year have to be the same. In this section, you're going to be still be depositing and investing, but in payments, not a lump sum. So that means that now the present value is always going to be 0 because we don't make a lump sum. So, for example, let's suppose that at age 25, Eileen starts depositing $50 a month into a retirement account that earns 8%. How much will her IRA contain at age 65? And then we want to compare that to the actual money that's deposited. So we have this list of numbers and we have to figure out what all these numbers are. The first thing we need to know is how many years will the money be invested? Well, she's starting at age 25 and she's going to retire when she's 65. So 65 minus 25 means that her account is going to be in effect for 40 years. The next thing that we'll look at is her interest rate, and it's stated pretty plainly in the problem that the account earns 8%. So we will enter the percentage as 8. So at this point I'm going to go second, x to the negative 1 to get to the finance calculator and choose the solver. And right now at n I'm going to put in 40. Now I'm not finished, but that's what I'm going to start with right now. Now, she has 8% interest. We've already said the present value is going to be 0. Let's go on to the next step. And the next step says, okay, she's going to make monthly payments. So that means her number of payments, which is what N is going to be her 40 years times 12 payments each year. So that means in total she's going to make 480 payments. And then those payment amounts are also going to come down here and be entered as 12 payments per year and 12 compoundings per year. And we're just going to default to having the payments being made at the end of each month. So then our next job is to consider what the next piece of information is. And the next piece of information is her payment amount. She's depositing, in other words, she's having money go out from her person and into her account, so that's negative. She's depositing $50 a month into her retirement account, so we enter that as negative 50. And then on the next slide, we make a note that we have entered the present value of 0. Because we are not making a lump sum payment, the present value would be entered as a 0. And the only thing that we have right now that we don't know is the future value. The future value would still be blank. So just to recap, 40 years times 12 months in a year means she's making 480 payments at 8% interest with no lump sum payment. Payments of $50 every month for 12 payments per year and compounding 12 times a year, and we want to know how much money she's going to have at the end of that period of time. So we see here the results of the calculator screens, and so that you'll understand how to do this. And this is a little tricky to remember. You don't hit the second button. It's actually the alpha button, the green button on my calculator. You hit alpha, which is underneath the second button, and then enter, and it will tell you the amount of money that she has in her account at the end of 40 years at that interest rate when she deposits $50 a month. And at the end of that time, when she's 65 and she's ready to retire, there will be $174,000, $174,550.39 in her retirement account. So that's, you know, a pretty good bit of money to have to retire on. You know, go Eileen, that's good. She's got some money to back her up for retirement. Now, one more step, it says, how much of that money did she actually deposit? Well, she actually deposited $50 a month for 480 months. So really only $24,000 of that money was money she paid into that account. The remaining $150,550.19 is interest on her investment. So really, yeah, go Eileen. She really had a good investment. Now, the hard part, I'm going to be honest, is you're probably going to have a hard time finding a retirement account that pays 8% right now. But you can still, if you hunt, you can find some good deals. But this is why it's important to start early and pay what you can. You know, you don't have to start out paying $200 or $300 a month to have a nice little nest egg when you retire. So there's our lesson on how to use the TVM solver, and we will practice with this more in class. But I made this so you'll be able to come back to it and refresh your memory on how to do this.